All right, now let's look into the internal forces at a specific point in a rigid body, for example, as you can see here. So think of point C as the point where we're trying to find our internal forces. Let's first take a close look at this rigid body, and let's understand that we have external forces, F1 and F2. Those are given to us usually. And then the first thing we do, and the things that you've done in your last 3 homework assignments, were to find the external forces that are not given. So the support reaction at A and the support reaction at B. And you will have to continue to do that for each upcoming problem now. This is really the first thing you have to do, and that's why it's so important that you're so proficient at finding support reaction, because the support reaction define the internal forces. And if you do not get the support reactions correctly, then you cannot find the internal forces correctly, in this case at location C. So what do you do after you have the support reactions? You would then go ahead and virtually cut the system. That's how engineers say that, right? So we would cut the system at location C, and then we can separate the system. So we would either look at the entire right side of the system or the entire left side of the system. And I usually call these things cut clouds. People give them different names, but pretty much what we do is we separate the system at the location where we're interested in the internal forces. And then when we cut this, so let's think, for example, of this cut. If I were to draw that, let's do that here on the bottom. If I draw that cut, then my system would really look like this. I have, of course, my reference fiber that I cannot forget. I have my support reactions and my external forces. So here I have F1, here I have usually RAY, and then here I have also in this case a force that in this case points to the left, but in reality it points to the right because F2 is pointing to the left, and so we're balancing that with RAY. And from now on you understand that I cut the system here, which is really at location C. So this is location C. And this system, of course, cannot be in balance because, yeah, maybe F1 is equal to RA1 and then it would all be in vertical equilibrium. But again, you would have rotation, so it cannot be. And by the way, F1 here would not be equal to RAY unless it would be a very special case. And therefore, there's not even a vertical equilibrium. So what you have to do is you have to bring in your internal forces, which now, by the way, are external forces, right? So by me cutting the system here, and sometimes I give this a name, like I call this here cut 1, and I call this here cut 2. And of course, here I have given cut 1. And because I have extracted cut 1, the glue here is now out of balance, and I have to put that back into balance. And the trick that engineers use now is, hey, what happens if I take that away? So the forces that I take away are the ones that you have seen before. I have a vertical force, I have a horizontal force, and I also have a rotation. And again, this here points actually in this direction. In this case, this has to go in this direction, and this has to go in the counterclockwise direction. Why? Because this is actually a right cut. And if there's a right cut, there must also be a wrong cut, right? No, I'm just kidding. That's actually a right cut versus a left cut. So here we would have a left cut. And so this definition here, as you will see on the bottom of this page, the definition in which direction these forces point is actually defined by the left cut or the right cut, but I will come back to that. But for now, understand that I have M of C here, I have V of C here, and I have N of C. And now I can calculate these. If all the other forces and dimensions are known, everything in blue here would be known and the lengths would be known, then I can calculate MC, VC, and NC. And I say it again, the trick that engineers use is we pretend that this is not there initially, and what is the imbalance that I have to balance or bring back into equilibrium by using these purple forces here. And hopefully you are looking at this right now and you say, this is actually an easy problem for me now because I can already calculate these forces. This looks exactly like what I've done when I solved cantilever problems. So when you were solving cantilever problems, all the forces were given to you except the force at the cantilever. And what forces did the cantilever balance? It balanced a vertical force, it balanced a horizontal force, and it balanced a moment. And this is exactly the same. So mathematically, you already have all the tools in place. You just need to understand how to apply it. So you know mathematically what to do. We just need to find out how we do it. But I think I already gave you a first insight. You cut at the location where you try to find your internal forces. You redraw your free body diagram. You are missing forces that can keep it into balance. Then you add the forces. You draw them into your free body diagram, and then you calculate them, and nothing is easier than calculate them by using the 3 equations of equilibrium. The sum of the forces in the y direction being equal to 0, the sum of the forces in the x direction being equal to 0, and the sum of the moments about the z-axis being equal to 0. Now, you already understand that I can, of course, draw the other side of this cut as well. So, for example, if I wanted to look at cut 2, I would just have the very same system that looks in this case then like that, with a force here and a sloped force here, which we called F2. This here would be RBY. And of course, this system as it looks right now is not in balance, but this would be cut 2. And this actually happens to be a left cut, which, by the way, is the right side of the system, right? So this is the right side of system. So the beam is really the right side here. So this is the right part, but because the cut is on the left side here, it's called a left cut. And now this, of course, is not in equilibrium. You can see that right now. So I have to bring in my external forces, which ultimately are the internal forces. But because I made the green cut there, I now actually have external forces, a vertical one, a horizontal one, and a moment, if you will. And of course, they now have to balance whatever I have defined here. So therefore, they point upwards, they point to the left, and they rotate clockwise in this case. And of course, they are also N of C, V of C, and M of C. And now the left side is in balance with the right side. This is always the case. And this is just shown conceptually here, but with numbers, this will come out to be the same, as you will see when we solve our example. Now, the picture here on the bottom is the same thing, just a little bit nicer. And you understand that, of course, it has the reference fiber missing. But other than that, it shows you the same concept. So let's use this picture here to clarify that we're talking about the right side with left cut. And here on the other side, we're talking about the left side with a right cut. So I say it one last time, we cut the system right here and right here. And of course, there's a left side and a right side to it. But with that said, I believe we now have everything in place that we need to know to conceptually solve these problems, except the one thing is the mathematical definition of when a value is positive and when a value is negative. But for that, I'm going to move on to the bottom of this page to talk about the mathematical definition of internal forces.